Okay, so it's not Monday, it is Thursday, and we just saw each other yesterday, and some of you I just saw a few minutes ago in lab and so forth. Today we're going to kind of continue what we left off with yesterday and binary trees. I'm also going to talk about this homework 2A provide. One of you, who shall remain nameless unless he or she wants to be named, so he made a suggestion to do this homework 2A provide business, which means that, and I sent you the email about it, so you probably already read the email, but basically you can go and provide your homework from last week into this new HW2A. If you change your makefile, it works out. You can provide into that and get the same feedback you would have gotten from the test last week when we handed the homework in, and you can fix your code. And we'll talk about why that's going to be important in a minute. We are not going to look at it. We're not going to grade it, whatever. You can provide as many hundreds of times if you want. Well, I think I have it up to 100 at this point, but if you need more, let me know. I hope you don't. But you can. Let's see. We're going to talk about the homework 3, which is coming up, and I'll probably have that out Saturday. We'll be doing a week and a half and something like that. That'll be hopefully kind of fun. And then we'll go into binary trees. Okay. I was going to have a Unix tip of the day, but the programs that I wanted to show you actually aren't installed on Unix. They aren't installed on the Unix we use, the Linux that we use. I can actually show you what I was going to show you. I wanted to show you a little thing called banner, which if you do banner, let's see. I think I got to do it this way. Echo, hello, banner. It actually, that is the O of a banner, like the hello. I think I said hello. That's the O, meaning the rest of it is like all the way up there, right? It prints out giant letters for you. Now, these days, who cares? But you guys are all too young to remember. You've probably seen it in like movies and whatever. Printer paper that was like perforated and had the little things on the side, and then if you pull it, you could pull one piece and it would be like all the pieces connected together by perforation. Well, you could print cool banners like that, right? And you could print these letters and giant letters and whatever, and you could use this to do that. So anyway, they haven't installed it, probably because nobody uses that kind of paper anymore. But anyway, the other one I wanted to show you was this this program that I didn't actually expect it to be on the thing. But if you say cowsay, right? Cowsay, right? High data structures, right? Right? It's a little cow that actually says hi data structure, right? Right? You can also say like what's the other one? Cow think. Moo, right? And then he actually thinks it. It's the little thought bubbles, right? So you can do that. For those of you, I'm struggling to come up with like new Unix things to show you, but I'll find some others. There are lots of others, but I thought we'd have some fun ones today. For those of you who have a Mac, and like I think it's like 95% of you guys. Does Tufts say you probably should get a Mac? Because most people do, but well, I guess it's a sign of the times. But anyway, if you just go in your Mac terminal and say, welcome to machine, and if you remember that you know that reference, you're definitely back in there. Right? That actually came through the speakers because your computer will talk to you, right? Say, I'm the computer, dummy. Right? So anyway, I every so often I'll be sitting on the couch and I'll like SSH to my girlfriend's computer and like make it say stuff, and she'll be like, "What the hell's going on?" and she has no idea what's going on. Yeah. I think the bigger question is why I can SSH to my girlfriend's machine, but she doesn't know. She doesn't know. Anyway. I don't know. I don't know if that makes it better, but anyway. Okay, so that's Unix tips. Not something you can do if you have a Mac. You can run. Well, you have to install them. Cowsay. I think you can find it. So, all right. So so this provide thing. So as I said, you can do this new provide. If you go to the make file and change where it says HW2 to HW2A, it will provide to the proper location. and you can get the same feedback as before. One of the things you will want to do, preferably before Saturday if possible, but not necessarily, I mean before you start working on the next assignment, is get your code for this homework 2 to actually work 100% for all the tests, including the ones we gave you and including the ones that Provide does, so that it will work in homework 3, because homework 3 is going to build on homework 2, okay, in the sense that it's going to be another calendar program. This time we're going to hopefully have it import from Google Calendar, right? So if you have a Google Calendar, you can export from Google Calendar and then import into your program. You'll have all your own events in there if you want, and maybe export back to Google Calendar if you want. It's also going to have multiple days. It's going to do things like deal with conflicts and overlap, like if two events conflict. And then there's another one where it's going to be like, hey, find a free block of time, right? I have to do that all the time when people email me and say, can I meet? I got to go. I do it manually, but it'd be kind of cool to have my computer just say, your free time is 3 a.m. tonight, or whatever, right? So we could do that. And I think those will be the big things for the assignment. We may also have something where if you do recurring events, how do you schedule a recurring event? Like you can't put every day as the event. There's an infinite number of days in the future, right? So you have to figure out some structure for that. But anyway, try to get your code to work for the assignment. Speaking about the homework grades, if you got did anybody not get an email from Bruce yesterday? Okay, if you didn't, and you should have, like you've already done the providing whatever and whatever, email me and I'll make sure I get you your grade. Okay, but for those of you who did get the grade, if you weren't happy with it, I apologize. I mean, I think we gave ample opportunity to come to office hours and things, but in the future, you guys will be doing more testing of your code to make sure that it's working for all the different cases, I hope. And if you do have a problem with the grade, like if you think I shouldn't have gotten this grade, for instance, somebody, I don't even know what class it was in, somebody had an extra new line somewhere in their print day or print event function or whatever it was. It was just an extra new line, and that ended up making like 90% of the other tests not work because everything that printed out was off by something. And then the TA who graded it didn't catch that there was some problem with that. So the TA said, oh, well, this is wrong. All this stuff is wrong. And so they ended up getting a really bad grade when they should have just gotten 1 point off for like the extra new line or whatever, right? So if you think you fall into that category, certainly email me. Come by. We'll figure it out. We'll look at your code. We are not perfect. The grading scripts are not perfect. So I don't want to penalize you. Yes?
Is it weird? I got my email on Friday. Does that just mean that my TA graded?
I think yours was probably what Bruce, you may be at the top of the alphabet. Bruce was testing something and sent it. So I think you got yours early. Yeah. So anyway, again, I don't want to penalize people for doing good work. If you were dissatisfied with your grade and you think, hey, I could have written a better program, come to office hours, we'll work on it. And if you can't figure out what the problem is, like let's say you can't and homework 3 comes and I don't want you using old bad code, so see me, we'll work something out. We'll either sit down and just figure it out, or I'll give you working code and take a couple points off or something like that. Does that make sense? For the old stuff? Okay, you had a question.
Yeah, what about if we got points off for comments? Should we go and fix those for the next homework?
If you got points off for comments, no, don't go. Well, if it was you didn't have any comments, you should probably go comment your code. Yeah, I mean, I doubt we're going to look at the old stuff in very much detail. It's just if it doesn't work, then you're going to be in trouble. So I wouldn't worry about those. But good question. Wouldn't worry about that. Yes. Yeah.
If I got points off for functions being slightly over 39.
I told you we wouldn't do that, didn't I? Yeah. Email me. I'll fix it. Okay. Yeah. That was in the. Yeah. If you got, Bruce and I have somewhat of a disagreement on this. It's not a big deal. I mean, I'm not going to take up points this time. Next time, make your functions under 40. How's that sound? Or whatever it was, 30. Make it under 30. We'll do it. But this time, email me if you got points off. What's that?
31.
Whatever, 31. All right. If it was 31 or more, I don't know. Anyway, yes, question.
Could you send us an email just explaining again how to do the homework 2A provide?
Sure. I mean, all you do, take your old code that you provided before, go to the make file, change the one line that says HW2 in it to HW2A, and that's it.
Okay.
And you reprovide, and then provide as normal. Make provide, and it's perfect.
Gotcha.
Yeah. If you try to provide to homework 2, it just will tell you it's closed. So
Okay.
either way. But
So we don't need to change the name of the folder?
nothing. Don't need to change anything.
Okay.
Yeah. Just that. Well, just that line. Okay. Anything else? I think if anybody, well, you can't tell. My little speaker might be going dead. Yes?
How strict are you going to enforce the 80 colors
For this time, if you got points off, I will undo those points. Email me. Next time, I will enforce it. Bruce is kind of convinced it's important. It's not that hard to make it, to do a new line. So yeah, same thing. If you got points off for column length. Other questions? OK. All right, back to binary trees. OK, this is just a little bit of review from yesterday that was already a review. But I'm just going to go through this. Binary trees, 2 nodes, or two pointers per node. One is to the left, one is to the right. And by the way, I learned this, like this one's left and this one's right, by doing like tours when I was in college, right? You know, because you got to go, oh, I'm on my left. You know. Sorry. Anyway. So 2 nodes, left and right. Okay, only 2, or 0, or 1. Okay. Sometimes we get these weird degenerate cases. We'll see a little bit more of that. Okay, but the depth of a binary tree is generally very good for dealing with accessing like down the list, because you don't have to go very far. Generally, it's a very shallow list, a shallow data structure, which is nice. Binary search trees, which we'll get to in a minute, are actually even better. OK, so yesterday I mentioned the expression trees. And I put this big one up on the board. But I thought it might be a good idea to go back and look at a slightly less extensive example, like basically 1 node like this, right? This just says this represents A times B. OK? The times is the operator that is the root of this little mini tree. A is the left node, B is the right node, and that's that. OK? A times B. If we want to represent this in infix notation, which is our normal, the way you think of arithmetic notation, okay, we can print this out using this kind of very relatively straightforward algorithm. The only problem with it is it over-parenthesizes. It does enough parentheses, and you can actually do it. But this algorithm will come up with parenthesis, parenthesis A times parenthesis B, parenthesis, right? That's what it's going to end up with. Okay, and let's see what it does. What it says is we call this an in-order traversal, which I'll show you what that means in a couple minutes. In fact, I've got a link for an animation of this that I'll show you as well. So in order does the following. It takes a node. In this case, we'll pass it like the root of this node. And if the node is null, okay, return if it's null. If it's not null, you print a left parentheses. Then you call in order on the left child. Then you print the actual symbol that you're talking about. Then you call in order on the right child, and then you print a right parentheses. Okay, that's actually not too bad for an algorithm. But let's see what it looks like. The hard part of all these recursive algorithms is figuring out where in the algorithm you are for what element, right? That's the hardest part about it. OK, so let's look at this. If we were to start out and say in order of the root of this node, OK, in this case, which is just the one that has the star in it. If we were to do that, here's what happens. It goes through and it says, is node null? No, node is not null. It's got a star in it. Print left parentheses. OK, so we print a left parentheses. Then it says in order left child. Okay, so that means call this left child. And so what's happening is we're now outside the in order function for star, and we are in the in order function for A in this case. Okay, so we started back at the top again. Is that node null? Nope, this node's not null. So we print a left parentheses. Then we do in order left child. Well, what's the left child of A? Null. So when it gets in here and it says in order null, it returns. OK, so then what happens is we're back here to after in order left child for A, which says print the symbol. Prints A, because A is the symbol for this. Then we do in order right child. Same deal as before. A doesn't have any right child. So it's going to go into the function it's going to return. And then we're going to say print right parentheses for A here. And then A is going to be done. Right? We're done with A. And we are back at the after we did the in order left child for star, because that's where we left off. We went here, did some stuff. Now we're back to here, but we're back to here after in order left child. Print the symbol. Well, the symbol happens to be star. because we're in this one at this line right here, print the symbol. Then we do in order right child. Star does have a right child, so we're going to do in order B. So now what's happening is we're doing like in order B. Right? And so we go into in order B and we start over again. Is B null? Nope, it's not null. Print left parentheses. OK. Same deal as with A. In order left child returns null, so we're not gonna basically go right over that one. Print the symbol B. Right? In order right child, there's no right child to B, so that one's not going to come back null. Going to come back immediately. And then print the right parentheses. And then we're done with, and then we're finished with B. And so where did we leave off before? We left off after in order right child of star, and then we finally have to print a right parentheses. Like that. OK, see how that works? Following that, doing that trace is an important skill. It's also kind of tricky, especially when you have recursion that's a little more deep and a little more stuff going on. But that's what we got. We got an infix overly parenthesized version. Questions on that? OK, good. Let's say we didn't want to print those extra parentheses. Right? If we want to, these ones are really stupid, right? The ones just around the characters, those are kind of dumb. We can do that. We can get rid of those just by putting a couple of a little check in there to say, if the node has a left child, that's when you print the left parentheses. Right? So in other words, it would say you would go to A, and it would go to A, and it wouldn't print a left. It would start it. It would print a left parentheses for star. So you do start with that first left parentheses. Then it would get to A, and A does not have a left child, so you don't print parentheses. You do end up printing A. You do end up printing Then you get down here, and it says, if a node has a right child, print the right parentheses. Well, A doesn't have a right child either. No parentheses. So that's getting rid of the one on that node that doesn't need the parentheses. And then you'd end up going back up to here. You would still print the symbol. And then, actually, that should be a star. Sorry. And you should you'd print the symbol and then get to B. B doesn't have any children either, so it also doesn't require the parentheses. And then you end up going back up to the star, which does require the right parentheses there, because it does have a right child. And that's it. So you get fewer parentheses. This would actually work. This would still put parentheses on a next set of terms that needed them. So if this had like extra stuff down here, it would certainly put another parenthesis in there. So it would still work, and you still don't need to worry about order of operations for this method. OK? Any questions on that? Just a little extra stuff there. OK, good. All right, we did this one yesterday, actually. OK, we actually kind of went through this one. We call it an in-order traversal. The reason it's called in order is because what it does is it starts here, and it goes, well, that's the first one, and then that's the second one, and that's the third one. Well, it actually goes, sorry, it goes here, this one, it comes back, then it does this one, then it goes down here and does this one, then this one, then this one, then this one. It's kind of going in order from left to right, all the way down as well. This in-order traversal, actually, I have this feeling that my program is not going to be up where I thought it was. I had to restart my computer for some reason. Let's see. Is this it? Maybe. Hang on. Yes. Java gives you all these warnings now if you try to. There it is. OK. Let's do a different one here. Let's make a new tree. That's a good one. OK. See this little thing here? So this is actually an animation program that somebody built, which is kind of cool, that actually shows you all of these traversals of these trees. OK? So watch this. If we do the in-order traversal, watch what it does. Okay, I'm going to click in-order traversal. The link is on the website. Okay, what it does, it goes that one, goes that one, goes that one. It keeps going left until it finds a node. And then it prints that, does that one. Then as it goes back up, it starts printing the nodes. Then it's got to go this way. And then it goes that one. And then it goes up and gets that one. And then down. And then it's got to do that one. And then it's done that one already. It's done that one already. It's got to do that one. So you see how this is going? If you don't, that's all right. I just keep following. What it's doing is it's always going left. And when it gets all the way to the bottom, it prints that one. And then as it goes back up, it prints the other one. It prints the ones on the way back up. Yeah?
Like the bottommost length on the left, because it just printed the 14 before the 12, and the last one in the second to the left.
Oh, yeah. Sorry. As it's going up from the left. You're right. Yeah. So if it gets to It goes down 98, goes to 70, goes to 14. Can't go left, so it's as if it's coming back up, so then it prints 14. Yeah, so it's always kind of going from bottom, going whoop, like that. Yeah. Okay. And then I think it got all of them. Well, not quite. There's 2 more. And then there, that one. Oh, there's 1 more, I guess. Yeah. So anyway, so that was the in order. This is actually, let's make a slightly different one that's not quite as painful. That's pretty painful. That one's pretty painful too, but we'll see what this one looks like. Okay. So anyway, that's in order. Okay, that's the in order one. We do not have to do the in order, like I mentioned yesterday, right at the end of class. Okay. By the way, this is if we fully parenthesize this. Whew, this is ugly, right? Not so good. If you want to fully, if you didn't fully parenthesize it, at least it'd be much nicer. Not great, but still not perfect because we have the order of operations. As I mentioned yesterday, the only reason we have order of operations is solely for the benefit of being able to get rid of a bunch of parentheses. If we knew order of operations, if we know that times has a higher priority than addition, then we can actually get rid of this one, set ones. We can get rid of the outside ones. Well, we probably could have gotten rid of the outside ones anyway. And then we can get rid of these ones too. So lots of parentheses you can get rid of, okay, if you know the order of operations. Yes?
Can you write arithmetic in C++
Can you write it in postfix? In C++? No. You can't do it in postfix. There may be some library you can write to do it that way, but no, you can't. It doesn't automatically convert for you. It couldn't figure that out. I mean, you could probably easily write that way. Like, you could write a programming language to accept that, but not in this one. Comp 50 people. Did you do postfix notation?
Yeah.
Did you use it a lot? Yeah, I mean, most of Lisp is actually postfix. And,
Dr. Racket is from
yeah. Right. So if you write a different programming language, like Lisp or Scheme, Dr. Racket, those languages happen to be based on a postfix way of thinking. Yeah, cool. Thanks. OK, so that's in order traversal. We can also do a different traversal. If we go through the list, or we go through the tree in a different order, we can actually get different results out, right? And we get different results, and in this case, we actually get the postfix that we're talking about. This is really easy. This is why postfix is kind of cool, because it's such an easy concept here, right? In this case, if we do the same exact tree and we use this algorithm for it, if notice null return Postorder, get left, Postorder, get right, then print the symbol, no parentheses necessary, and it comes out as postfix. Let's see. If we do Postorder of the first one, okay, it does the left one, A, and then A doesn't have a left or a right, so it just prints out. And then we are now here in the star one, right? So it's going to be Postorder of get right, which is B. B goes here. It doesn't have a left, doesn't have a right, so those return immediately, and it prints out B. And then it returns after. Now it's after this line in star, and it prints the symbol, which is star. Postfix. No parentheses necessary. Okay? Kind of cool. That kind of traversal, okay, it's called Postorder traversal. And you can see that the order this is going to go. It's going to start at the top node here. And remember how we did postfix before with the stack? And remember how a stack is a first in, last out data structure? Well, it turns out if you look at this, what's the first thing that's going to go into this recursive algorithm? This little plus. And it's going to have to wait around until everybody else gets done and before it gets printed. So that plus is going to end up the last one here because it's a first in, last out sort of algorithm. So watch what happens. It goes here, it starts here and goes left, 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 print. OK, we got to go back, but we don't print anything yet. We go right down this one, and then we go left down this one. Oh, can't go anywhere here, print. Go up here, go right, print. So we're always printing at the end before we go back up, before we back up the tree. Okay. Let's see if this one makes a little more sense on the diagram here. So this one is the Postorder. Okay. Got to keep going down before it gets there. Gets to the bottom one there. Doesn't print this, or prints that one because it's no right there. Okay, prints that one, no children. Prints that one because it's done with the 2 children. Goes to that one, that one, that one, that one. Comes back up, prints that one, prints the next one because it's done. goes back up, prints this one, skips 18, and then goes down, left, 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 print, etc. See how it's doing that? If you don't, that's all right. Watch it a few more times when you get home or whatever, and you'll figure it out. But it's always printing after it gets done, looking at all of the left and right children it can of a particular subtree or node. Make sense? I hope so. If it doesn't, I'll be happy to chat with you about it. But it's just the way we're doing the order. This is also called a depth-first search, too, by the way, okay, which is what we did for the maze algorithm before. OK, so that's postorder. Guess what? There's other kind of orders as well. There's a prefix order or a preorder traversal. Start here, print immediately, print immediately, print immediately. Go back up, print immediately, print immediately, print immediately, etc. Right? And that's the preorder direction or way of doing it, which is, let's say, preorder here, right? I'm not going to make you watch this whole thing, but see how every time it gets to a node, it just prints it. That's the first time it touches a node, prints it. And that's in this prefix. This ends up with being prefix notation, which is not as helpful as postfix, as it turns out, for arithmetic, which is one of the reasons we don't use it. OK? All right. There's another kind of traversal. Now, this one's kind of cool. This one is called a level order traversal, which means it goes level by level. It's going to go this one, then level 2, this one, and this one. Then level 3, this one, this one, this one, this one. Then level 4, this one, this one, this one, this one. Then level 5, this one, and this one. Okay? This, in order to print out, you actually require a queue to process it. Because basically what you're doing is you're saying, OK, I need to push this one on, and then push this one on, and push this one on. And then at the end, and you're going to do all this pushing, and then you're going to pop in the ones that you pushed on first. Because this one needs to come out first. And then this one needs to come out second, and this one needs to come out third. So it's a first in, first out situation. Otherwise, there's no way. You have to keep record of where it was so that you can get to its children. So that's what the queue is actually necessary for. Okay? That's what you need the queue for. Let me show you that one too. This is also known as a breadth-first search, and I'll explain what that means in one sec. There it is. This one is called level order. So it's going to go that one, and then that one, and then it's going to sweep over. It's going to kind of cheat. It's going to go that one. It doesn't actually have to go. It actually turns out it doesn't have to go back through the top like the other ones because of this queue that's storing all these nodes for you. Okay, so it can just go bing, 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 all the way down each level. Okay, this is called a breadth-first search, B-R-E-D-T-H, as in what lengthwise search, right? It does this way before it does a depth search. So that's the two differences. Okay, breadth versus depth. Yeah.
And does it do this by having horizontal pointers?
This does not need any extra pointers. What's happening is you're putting this into a queue, and then you're putting this one into a queue, then you're putting this one into a queue, and you're doing all the little ones into a queue, and then you're printing them all out. In fact, what happens is this one actually gets printed, and then, or you put it into a queue, then you take it immediately out. And then you've got this now recursive algorithm, or this, it's not even a recursive algorithm, it's just a loop that goes, do I have any children? Oh yeah, there's a child there, push that child, and then print this, right? Or print it and then push the children. And then it goes to this child and it says, oh, does it have children? Yes, push that, print that one. Push that, print that one. Then there's 4 more things in the queue. Pops this one, does it have children, et cetera, et cetera. So it's a nice algorithm, but it does not require any other pointers. Yep. It actually may require a pointer to pointers, which we'll get to in a few minutes. But it does not require other pointers themselves. Well, kind of. It kind of does, but not in the sense that you asked the question, I don't think. OK. All right. So let's do the following. Let's go backwards. Okay, here's what we're going to do now. We're now going to say, instead of going from the tree to the postfix notation, let's go from the postfix notation into the tree notation. Okay, I think we can do that. Here's the algorithm for this. Read the expression one symbol at a time. OK, we always do that, right? We're going to have this is our symbols that we're going to input. We're going to read A, then B, then plus, then etc. If the symbol is an operand, and an operand is like a letter in this case, not an operator, it's an operand, okay? Create a one-node tree. We can do that. And push it onto the stack. We have to use a stack for this because of the order of the way we're doing it. You'll see how it works out. It's actually fairly simple. But we're going to push the operand onto a stack. Oh no, my pointer's dying. Batteries again. Dying. There we go. Create a one-node tree, push it on a stack. If the symbol's an operator, pop the two things that are on the stack, okay? And then there are the trees themselves. Remember, we made them one-node trees to begin with. And then form a new node whose left and right children are T2 and T1. This is pretty cool. We're going to have two trees that are pushed onto the stack. We're going to merge them together using the operator as the new root. I'll show you what that looks like in a second. Okay? And then push that new tree back onto the stack. Now we're just dealing with pointers themselves. Yeah, Manvi.
I'm just wondering, so if you go into the wrong child, say, is there a way to pull?
Good question. If you go into the wrong child, is there a way to pull? Because the trees are more or less by definition singly linked, you can't go backwards in them. No. You could probably have a doubly linked tree of some sort, which means you'd have to go back up to your parent. I mean, you could do that. We generally handle that with recursion, and we write our algorithms right. But good question. Yeah, very good question. OK. All right, let's see how this actually works. OK. Here's our stack. Boom, 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 boom. Right? It's a stack. And it's instead of going up, it's going to go this way. This is the top of the stack. OK. Here's the algorithm in action. We are going to read A and B. OK. And because they are both operands, we're going to push them onto the stack. Okay, so A is now, well, we're going to create a node, a binary node tree out of them, and we're going to push them on a stack. Is this a tree? Sure it is. It's just one node. It's the root of its own tree, and there's no children. Okay, same thing with B. All right, so we get A and B. We push them onto the stack. Then we read the plus here. Okay, and the plus says pop two things from the stack and make the first one that you pop the right-hand child, and the second thing that you pop be the left-hand child of the new node that you've created with the operator. Right? So to go back and just one more time, you're going to pop B, pop A, and create a new node, a new tree with A and B as the right or left and right of the new tree. Everybody good with that? Okay. We see C, D, and E. They're all operands, so we push them on. Push, push, push with new trees of 1. Then we see a plus. What happens with the plus? We're going to pop this one and pop this one, make a new tree, and push it back on, and the tree is going to have a plus at its root, like that. And now you see what we've got here. We've got a tree here, well, 3 trees, one here, one here, and one here. These ones happen to have multiple nodes in them. Okay? All right, when we see the times, what are we going to do? Same thing. We're going to pop this tree, which means this whole thing gets popped off, and all you have is the root. And again, what's happening here, all of these things in here are just pointers to the trees. Now, aren't these pointers themselves? They actually are. So as it turns out, you've got a pointer to a pointer. And pointers to pointers are important in C++ and C because we use them a lot for things like this. Here's how you actually declare a pointer to a pointer. Okay? You would say something like binary node, right? Star, let's say, I don't know, I'll do it this way. A node. Right? That is, well, actually, I shouldn't even say that. I should probably say something like stack, because this is our stack, which is going to be a pointer to pointers to binary nodes, which is like 2 levels of indirection. Now, when you're doing C and C++, if you ever get to a point where you do star, 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 stop, because you're probably doing something wrong. right? I've never in practice seen anybody successfully use star, star, star and really figure out what they mean and do it effectively. That would mean a pointer to a pointer to a pointer, which it means something, but it's a little crazy. You guys know in physics how we've got length, you've got distance, and then you've got velocity, and you've got acceleration. And you know there's more after that, right? There's as many as you want. The next one is called what? Jerk, right? It's actually called jerk, and then I don't remember what the next one's called. Snap, that's it, yeah. If you're getting into like jerk and snap in physics, you've probably gone too far, right? Although, I should say I've seen some cool videos of little mini helicopters, those little like tiny little quad rotor helicopters doing amazing acrobatics, and the paper that goes along with that, it's a research paper that goes along with that, gets into the fact that they needed to use jerk and snap and all the like 2 or 3 other levels to actually figure out the right math to get it to work. But most of the time you don't need those things, right? In most cases you don't. Most of the time you don't need anything more than a pointer to a pointer. So if you find yourself doing that, back up a sec and say, did I really mean to do that? Yes, Allison.
So the plus sign is a pointer, but it also holds data.
Well, yeah, be careful. The plus sign is the symbol. Like this is the symbol that's inside this node right here. And this node has a left pointer and a right pointer. So if you look at, if you take the plus, it's got 3 components to it. It's got a symbol, it's got a pointer to the left node, and a pointer to the right node. And I probably should have boxed those because they're not actual, whatever.
So it's both a node and a pointer.
Well,
Like when you said it's a pointer.
yes, it is a, well, yeah. I mean, there is a pointer that is pointing to this node somewhere in memory. The node itself is somewhere in memory, right? But it's not in the stack. It's got a pointer saying, there's the node over there. So somewhere in memory, somewhere in memory, there's a structure that's called the node for this plus. And it's got this, and it's got a left, that points somewhere, and it's got a right that points somewhere. And that's off in memory somewhere, right? Okay? You've got a pointer that you've created that's called that's like called binary node or whatever that resides somewhere else that we've pointed there. What you're doing is you're saying the pointer to this one goes into our stack. So that's kind of what it is. It's like a double. It's a 2 levels down is what it is. Okay. So that's what it is. You've got a pointer to that memory location that holds the stuff. We're holding the pointer of pointers instead of the pointer to the stuff. So it's kind of a double link in that sense. Yes.
And this would be declared as a dynamic.
This could be declared as a dynamic array or a linked list, whatever you want. But yeah, in this case I'm thinking of it as a dynamic array, yes, or an array in general.
But if it's a static array, isn't it
Yeah.
just a single pointer?
If it's a it can be a double pointer as well. Yeah. It's in some cases it just makes it easier so you don't have to actually copy data around. I mean, I guess you could do this with just a pointer to nodes themselves. That's fine. The way I did it on the website, which if you want to download the code, you'll see that it's pointers to pointers, and you'll see why. But yeah, I suppose you could just have this guy pointing to, or the stack pointing to the pointers to these, or pointing to these nodes directly. That's fine. But I didn't happen to do it that way. It's kind of up, depending on what you want to do. Yeah, there is kind of a middleman in this sense. Yeah. But you already have that pointer. So instead of kind of directing to another point, you direct it to that pointer that you already have, and it just makes it a little bit easier. Except conceptually, I suppose. But take a look at the code. If you have any questions about it, stop by. We'll take a look at it. All right, so we are to the point where we have done the tree to this point. We've got 2 stars, 2 asterisks left. We see the next asterisk, and what do? We pop this tree, and make a new node that connects. This is the right child, this is the left child, and there we go. Right, and then we push that back on the stack. And finally, we've got that other asterisk, and same deal. Okay, we pop this one, merge them with the asterisk, and end up with one thing left on the stack, which is great, and that is our tree representation of the postfix notation. Okay. Any questions on that? You can go back and look at them on the slides if you want and kind of walk through it again if you do have any questions. Okay. All right. If that's enough, I think that's enough for that. The next thing we're going to talk about. So we've kind of been introduced to binary trees. Now we get into the real cool stuff here. The binary search tree is a special kind of binary tree that says the following. For every node, x, all the items in x's left tree are less than the item itself. Don't worry about duplicates right now. Everything in the left tree is less than that item at the root of that subtree or tree. Also, every item to the right is greater than the item in that node at the root. Okay, that's all it means. This is an invariant. Okay, and we say it's an invariant because whenever you're dealing with these binary search trees, when you get finished doing something to the tree, modifying it in some way, it better come out such that everything in the left of every node is less than all those nodes, and everything on the right is less than or is greater than all those nodes. Okay, that's what we call the invariant. You got to make sure that holds when you deal with this tree. Okay, any questions on that? We're going to do an example now to show you what I mean. Okay, question, Margaret. Good question. The root doesn't have to be anywhere. The root can be anywhere. And as it turns out, binary search trees can come into some very degenerate cases that we don't really like. Okay, and I'll show you that in a minute as well. Okay, very, very, very good question. We will learn next week about balancing these kinds of trees, which means making it so that they don't end up in these weird cases. Okay? All right, so here's an example. The tree on the left is a binary tree. The tree on the right is a binary tree. The one on the left is a binary search tree. The one on the right is not a binary search tree. Why is that the case? Yeah. Yeah, so the 6 here, on the right everything's bigger. On the left, this is all to the left of 6. Even though 7 actually physically resides over here, it's actually in the left tree of 6, and it's bigger than 6. So not a binary search tree. Okay, you would not want to build this and call it a binary search tree. The nice thing about binary search trees is they have an even better average depth than a straight up binary tree. As it turns out, in the process of building binary search trees, you build them in general such that the average depth, how far down it is on the order of the logarithm of the number of nodes. And that is why binary trees are actually so great. Because logarithms grow very slowly. Okay, that's the whole point of them. Logarithms grow slowly. And they grow slowly. If that's true and we're going down a tree to get somewhere, it doesn't take that long to go down the tree, right? Because we're doing the log of the number of nodes to get down, and that's a very small number, which is nice. If you have like 100 nodes and you're doing the log base 10 of that, right? You only have to go down 10 levels, even though there's 100 nodes. If you have 1,000, you only have to go down 100 nodes, right? So it's much, much nicer. Okay? Is that right? 100 log of, yeah. No, sorry, I lied. I did lie. If you have 100 nodes, you only need to go down 2 levels, don't you? Log of 10 of 100, yeah. Mainly we do in base 2. These are actually base 2, so I shouldn't have used 100. But if you have 2 nodes, log of 2 in base 2 is 1, correct? Yep. Log of 4 is 2, 8 is 3, 16 is 4, etc. 32 is 5, 64 is 6. So if you have 64 nodes in a binary tree, the odds are you only have to go down. The average case is you only have to go down 6 nodes. Okay, so that's a very nice property to have. Okay, questions on this? Yeah, James.
So will we discuss what happens if you have 2 of the same?
Yeah, two of the same is a special case. What we're generally going to do is not insert them in there. We're going to just keep a count of how many nodes there are of that number, if you want to. Sometimes we just throw it out. If it's already in the tree, who cares? It's already in the tree, throw it out. Because a lot of times you don't need to worry about that. But if you do need to worry about it, then you could either keep a separate list of how many per node there are, or you could have each node say how many count there are. Doesn't matter. That would take a little more memory, but you could do it that way. So yeah, good question. Okay. So we can do some operations on binary search trees, right? We can do some operations. There are some easy methods that we can do. These are the easy ones. Find min, find max, contains, insert, and then there's one that I'm calling hard. It's not particularly hard. It's just harder than doing the other ones, and we'll get to what that means in a minute. When we say that the invariant is that the things on the right are greater than the things than the node itself, what that actually means is you have to have some way to compare two nodes. If they're just integers, that's easy, right? If they're floating point, all right, we have a little trouble comparing floating points, but it's not the end of the world. If there are other things, right, that don't have numbers associated with them, you have to figure out some way to compare them. And it's probably going to be a numbered system. But if it was letters of the alphabet, right, well, you'd have to number all the letters and use the numbers of the letters. We generally do that in what's called ASCII, right? But you would have to have some way to compare them. If it's an object, let's say it's some record with some employee or something, it might have the, I don't know, you might have the birth date of the employee or sort it that way or something like that, or salary or whatever. But either way, you're going to have some way to compare if you're going to do a binary search tree. Okay, so that comparison's the part that we're most concerned about. Okay, let's look at some of these methods. This one is so easy, all of you can probably figure out exactly how to do this. If you can't, that's all right. But if you can't, but you probably can. How do we find the minimum value in a binary search tree? I heard lots of people say it. Somebody raise their hand and give me an answer. Yeah, Susanna. Go to the left. Just keep going left, 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 until what? No. Until you hit a null. When you get a null, right, that means we're there. And that's it. I know, good job. Right? So you start here, left, left, up, no, no, that's the minimum. Conversely, or I should say in the same way, right, we have find max, which is exactly the opposite, right? Go right until you can't go any farther, and then there's no there. That's the one that's the maximum. It's got to be. That's the way the tree gets built. If we tried to put a 9 in here, right, it would be 9 would be to the right of 8 and 10. And this is where the degenerate cases come in, right? If you are putting items into a list or into a tree, and you did 1, 2, 3, 4, 5. We'll get to that when we do insert in a few minutes. 1, 2, 3, 4, 5. You do 1. Well, then 2 is going to be here, and 3 is going to be here, and 4 is going to be here. That's what now? Not really a tree anymore. It's what? It's a linked list. Angled funny, all right? But it's just a linked list because you haven't actually put anything in there. If you're going to put like 2.5 or something, sure. Then you go and put 2.5 somewhere else in here, right? Which we'll get to how to do that in a second. But you can end up with degenerate cases here. But it's always because everything to the right has to be bigger. And if you're always bigger, then you end up with these crazy cases. Okay? And again, we'll talk about how to balance these things next week. So find max, start at the root, go all the way right until a node doesn't have a right child. That's the one you're looking for. Okay? All right. Now contains. So what we want to find out is, does the tree, T, contain the value x? This isn't too bad either. Does the tree contain the value x? How would we figure that out? Somebody who hasn't answered in a while, yeah?
You could compare it to the node you're at.
Compare it to the node you're at.
So if it's smaller, go to the left, and if it's bigger, go to the right, and just
Keep doing that until what?
until you either hit the node or you're at null.
Until you either hit the node or you're at null. Perfect. Okay, so that is exactly right. Let's see, if first of all, if it's empty, return false, because we're going to do this recursively, right? And then if it is the value, return true, because we found it. What we're trying to do is see if this contains, it was just going to be true or false. And then recursively call either left or right depending on x's relationship to t, if it's smaller or larger. Perfect. OK, so if we wanted to find 4, well, let's see, is 6 4? No. Well, first of all, is there a node? Does the node exist? Yes. Is 6 4? No. But 4 is less than 6, so we go left. We check it. Is 2 null? No. Is 2 less than, or 2 equal to 4? No. 2 is less than 4, or rather 4 is greater than 2, so we go right. And then 4 is not null, but it is 4, and we found it. Right? If we want to find 7, let's see. We go here. We go right because it's bigger. We try to go left. Null. It doesn't exist in the tree. Easy enough? I think that's pretty straightforward. Okay. How about insert? Now, this is where it gets a little fun. Okay. Insert. Any ideas how we'll actually insert a value? A couple people have answered already today. A couple people haven't. How about somebody who hasn't answered? How would we insert into this tree? Think about it for a sec. What we need to do, we need to keep the invariant true, that everything on the right is bigger, everything on the left is smaller. I'll give you a hint. It's very similar to contains. Yeah? Yeah, do the exact same thing as contains. In other words, check and see if that's the value, right? And if it is, that's a special case. And then if not, go where it should be, bigger or smaller. If it's 7, it's going to be bigger than this one. Goes to here. It's not 8, so it's going to be to the left. Well, there is nothing to the left. That's where it goes. Perfect. OK? So that's fairly simple. Yes?
Do binary search trees have like a place to put values that are equal to these?
Right. We were just talking about that. The question is, do they have values where, or how do you store values that are equal? We said this is a special case. OK? If it's equal, you can either keep a list of duplicates somewhere else in some other list that just is an array that says the list of duplicates. And that's nice. A separate list is nice because let's say you have a million numbers and only 3 of them are duplicates. Well, you've got a tiny little list of 3 that says, hey, these are the duplicates and how many there are. Right? Or you could do each node has another thing besides the object, the left and the right, that says the count, which could be how many of that there are. The problem with that is what? Let's say the same case where you have a million values and only 3 of them are.
You're just going to have a lot of counts that are only 1.
You have a lot of counts that are 1, right? Yeah, so they're all going to be, you're going to waste memory in that sense. But yeah, but that's how we would probably do it. You could make a decision that says if it's even, put the equivalent one on the left. If it's odd, put it on the right. And then just know that your tree is going to look a little strange and have like 8, 8, right? And then you'd have to know where to put, you'd have to go and know where to put 7. You'd have to walk down the 8s if there were and put, I mean, it would be a slightly different, you'd have a slightly different set of algorithms to do it if you actually wanted to keep it in there. And the tree would be too big. I mean, it would be bigger. So not necessary. Okay, good. Other questions on that? OK. So let's see. We did find min, find max, contains, and insert. And those were what I said were the easier ones. OK? Oops, and I forgot. If the node traverses null, go ahead. That's where you insert it. Sorry, who's asking? Oh, yeah, go ahead.
What if you have to insert, I want to say 5, but then I realize that it fits in right after 4.
Yeah. Well, OK. So what if maybe your question is what if you had to insert a fraction? No? I mean, fractions are the same. It doesn't. Yeah. Oh, good question. Would you ever have to insert between 2 nodes? Why would you ever have to insert between 2 nodes? Because you've always got a left and a right for every node. And you would go down a path that's always in the right direction, so the correct direction. So yeah, it turns out you don't ever have to do that. Good question, though. Yeah, Susanna. Yeah, 7 goes, 6 is bigger than 6, it's smaller than 8, it goes right here. 5, how about 5? Smaller than 6, down this way. Bigger than 2, down this way. Bigger than 4, oh good, there's a spot, boop, right there. Good? Okay, yeah, Tara.
If you were inserting the numbers in a different order, you would have a different tree.
Totally different tree. Yep, absolutely. In fact, a binary search tree is not unique for the numbers that are in it. It certainly is not unique, right? I mean, if we were going to now, let's say we're going to insert let's say we're going to insert 7, then, well, this is a tough one. This is a tough example.
Inserted 3 before you inserted 4, for example.
Yeah, if you had inserted 3 before 4, right, it would have looked, the part that, well, it would have looked like this. It would have been 6 and 2, and then 1, and then let's say 8, and then 3, right? So 3 would have gone here, and then 4 would have gone here, right? And that's what it would have looked like in that case. Yeah, so totally different tree. And in fact, if you did 1, 2, 3, 4, 6, 8, remember it's going to be a line straight down. If you did 8, 6, 4, 3, 2, 1, it's going to be a line the exact opposite way. It's going to be a linked list going the wrong way. Right? So yeah, so these can turn into degenerate cases pretty easily. And again, we're going to talk about how to balance those coming up. Okay, good questions. Anything else? All right. Okay. How do we do remove? Lots of possibilities here. Let's think about this. Well, first of all, let's find out what the possibilities are. What would be the easiest thing to remove? Yeah. Make sure it exists. If it exists, yeah. If it doesn't, if it exists, if it doesn't exist, we're going to eventually find where it should be and then say, oh, not there anymore. We're going to get to the leaf or something. Good. Okay. What's another case? If it doesn't exist, what's another easy case? Let's say, yeah. If you're at a leaf, if you're at 8 or if you're at 3, how hard is it to delete those, right? Just say 6 doesn't have a right pointer goes to null, and then delete 8. Done. Yeah, Suzanne? No, go, okay. Yeah.
Can you you can just delete any of those nodes in the tree, right? Like those leaves,
Any of the leaves? 1, 3, and 8.
delete it, right? Because they're
There's nothing they need to.
dynamic anyway.
They're dynamic anyway. Yeah, they're pointers. They're pointers to nodes, and you would have to delete them using your destructor or whatever. I mean, you'd want to do it properly, but yes, you just delete them. Yeah. You don't have to. I mean, there's no other magic involved. It's just deleting it in that case. Yeah. Okay. So leaves are easy. Definitely an easy case. Okay. What's a harder case? What if you wanted to remove something that has 1 child? Let's say we wanted to remove 4. How do we do that? Somebody who has an answer. Somebody on this side who hasn't answered in a while. In the back. Yeah, Kobe, what would you do? Let's think about this. If you're going to get rid of this one, and that one's gone, right? What happens to 3? You have to replace which one? The point. Well, yes, you do. You can't leave 3 hanging. So if you got rid of this, something points to 3. What's going to point to 3 now? How about 2? What's that? Right, if you just took out 4, you need to do a replace. Think about how we do linked lists, right? Think about how we do linked lists in the sense that if this was a linked list, how do we get rid of 4? Well, we say that 2's next pointer points to 3, and then that's all we need to change, right? And then we delete 4. That's how you got rid of a linked list node. It's exactly the same thing, except there's a left and a right involved. So all you do for a node with 1 child is get rid of that node and replace its parent's pointer in that direction to its child if there's only 1 child. Yeah.
And this all already assumes that in this case 3 would never have been a number that might have been bigger than the root of the entire tree, right? Because then you have to inherit.
Absolutely. Well, and that's the whole point of the invariant. Yeah, the question was if we're assuming that 3 is in a proper case and that it is a binary search tree. We have to start with binary search tree, otherwise the whole thing falls apart. So is this a binary search tree? Sure. 8 is bigger than 6, 2, 4, 3, and 1 are all less than 6. 4 and 3 are greater than 2. We're done. Right? Okay, so it is a binary search tree. And yes, if you do this out, it will never mess up in that case. Okay, so those are the easy cases. If it's null, it's easy. If it doesn't exist, it's relatively easy. It's easy. If it's a leaf, very easy. If it's a node with 1 child, slightly harder, but not difficult. What if, okay, so 1 node, just delete it. Node has 1 child, bypass the linked list. So how did we delete 4 in this case? We said that. We take 2 and point to 3, just delete 4 like that, easy. If a node has 2 children, that's the other case, right? I know a couple people are like, oh, I get it. I know how to do it. Let's think about it. Think about it for a minute before I start opening it up. Let's say we wanted to remove, let's say something that has 2 children here, like 2. We want to remove 2. What has to happen? Think about it, and then I'll let somebody answer it, or think about it. By the way, there actually are multiple solutions to this. This is not a one solution fits all sort of thing. A couple hands, couple hands, couple hands. Good. Try to think about what might have to happen. What might have to happen here? Let's see. All right, how about an idea? You had your hand up first. Yes. Yep.
Find the greatest node without a right child on the left side. And then move the...
Find a greatest node on the left side without a right child?
Yeah.
Okay, and then what? Let's draw this and see what you mean in this case. So I'll redraw. I probably should have left it. OK, so we have 6 and 2, and we want to get rid of 2. And that goes to 1 and, let's see, 5 and 3, and then 4, and then we've got 8 over here. OK, so that's what we've got right now. Now, what you're saying, find the...
Well, first, I guess we have to check if it's greater than or less than.
Right, which one did you want to remove? The greatest one on the left tree that doesn't have a right child?
Yeah, it doesn't quite work out.
Oh, it doesn't work out? I mean, the greatest one that doesn't have a right child would be this one, right? And then you're saying, like, replace that one here? OK, if you did that, what would be the problem? Would there be a problem? Yeah, the 1's still got a problem, right? The 1 has to go somewhere, right? You'd have to figure out where in here it goes. And you don't try not to do it too low. Good idea. Very good idea. You're getting there. Go ahead, Tara.
Could you, for all of the branches below, could you create like a stack and then insert them starting from where you delete them?
Could
Like,
you?
if create like a stack of 1, 5, 3, and 4,
Uh-huh.
and then you reinsert them starting.
Oh, OK. So what you're saying is you could go and say, OK, if I want to just get rid of all these things, put them into a stack, and then reinsert them because we know how to insert quickly.
Yeah, but you want to
Using-
insert from where you deleted it. So you don't like,
Sure.
6 wasn't necessarily the root, but
Yeah.
it was like way bigger.
Right, somewhere else. You want to insert it right there.
Yeah.
OK, I believe that would work, right? The problem with that is, let's say you have 1,000,000 nodes down here, right? You've got to have a stack that's going to fit 1,000,000 things and then do all of them and run through all of them. And it's probably going to take a while. But I will buy that that works. That's not a bad idea. In the back, you had a comment. No? OK. Somebody else? Yep.
If 2 is on the left side of 6,
If 2 is on the left side of 6, OK.
then everything to the left of 2 should also be on the left of 6.
Yeah, fair enough.
Everything on the left,
So should all the rest of it, though.
yeah. Yeah. So you connect the one on the left of 2 to 6 if 2 is on the left, or one on the right if 1's on the right. And then you connect the one on the other side you do not connect to the one you disconnect.
OK, I'm not quite following you. And it's never going to make it on the tape, by the way. But let's see what this means. You're saying I'm going to do this. I'm going to have 6, and 8's not going to change, right?
No.
OK. 1 connects to 6. OK. And then what connects to 1? Right. What's that? If who's right? Yeah. What if this one had something? Yeah. Then we're in trouble. OK. Susanna, what do you think?
It's not known, start searching through like the right side and see if the right side is greater than or less than 5, and then case 5 accordingly.
Sure, you could. So Susanna's saying, look, start searching through here, find out where it goes, and sure, you could do that. But then you got to do more searching, and you've got to do all this. Like, there's actually a much easier way, as it turns out. But the searching is a good idea. Yeah. Yep.
I think because it's invariance, right? So 1 is surely less than 5.
1 is surely less than 5.
1 is less than 2, and 2 is less than 5.
Yeah, sure.
So because the right side of 5 is always more than 5, right?
The right side of 5 is always more than 5, yes.
So 1 is less than you can compare 1 to 2. The left not 5. So just going down.
OK.
1.
Yeah.
With all left.
Yeah. What if this had been Let's see, how can I do this? What if this had been 0? It wouldn't have been 0, you're right. OK, so you're saying this has to be bigger than this one, right? Yeah, OK. All right, so you're saying what? Take this one and what?
It may not be bigger, but you have to compare it.
OK, all right, all right. I like it. OK, more hands up. Yeah, go ahead.
What if you just like arbitrarily, you can kind of do it with either side of like with either the left side or the right side, you just pick one and set 6's pointer equal to that one, and then the other one you just pop it off and like set it at the end of whatever you
Would it necessarily go at the end somewhere? I'm not. Would it? OK. All right. So you're saying pick either 5 or 1? OK, and put it here, and then do what?
and then just put then if you
OK.
take it from the left side, just put everything on the right.
6. Hang on. Let's say we picked 5. 6, 5, 3, 4, and then we got 1 hanging out here. Where's it going to go?
Put it up. Three's on the other side.
Right here? What if 5 had, oh, sorry, 3 is on the other side. Sorry, I lied. You're right, you're right. Sorry. 3 is here, and then 4 is here, and then you're saying 1 is going to go here?
You just go down and find like
OK. On the end of 4? No, 1 would have to go here,
find
right? Because it's got to be less than 3.
a left that's no.
Ah, OK. OK, so that's not a bad idea. So whichever one has a left that's null. OK, I like that.
It's like a leaf.
Yeah, OK, OK. A couple more. I like all the, yeah, in the back. We haven't had an answer back there.
Okay. So what if, all right, we already established that the node to the left of 5 has to be greater than 1.
This one has to be greater than 1, yes.
So what if you went right and left, and then went until you found a leaf, and took that one and replaced it 2 with that?
That one.
Yes.
And replaced that one with up here?
Replace 2 with 4.
Right, so then you're saying this is going to become 6, then 4, and then 1, and then 5, and then 3, like that. I bet that looks like it would work for this case, as long as. Oh, you're right. 3's in the wrong place in that case. Ah, almost. Thanks for keeping me on my toes. OK, lots of different answers. Who hasn't answered in a while? Dylan hasn't. Go.
All right, so we take we're deleting node 2, right?
Yeah, we're deleting node 2.
It's a little bit difficult to explain with
Uh-oh.
this case because it's limited.
Yeah, 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 yeah.
Bigger tree would be, you would cover more cases.
OK.
You replace
Bigger tree would cover more cases,
the
yeah.
node 2 with its current left node.
OK,
But
so before we do that, OK. Before we replace 2 with its current left node.
Suggestion? Let's make it the big tree.
No,
Right? Start with 1.
I think you're going. I think you're going down a path that we don't have time for right now.
What
But
we do is we replace the node to the left, the node that we're deleting with the node to the left of it.
OK, so this is going to be 1. We're replacing the node to the one to the left. Yeah.
We're going to take the node that we're replacing, the deleted one, our new, so that the replacement, we're going to take the replacement, right?
This is this was the replacement.
Yeah. We're
Okay,
Gonna take that.
yeah.
If that has a left pointer, right? So
Okay,
if it has things
if-
that are smaller than that,
yeah.
it would be difficult in this case.
Yeah, yeah.
Then what we want to do is we want to make, if it has a right pointer,
Yeah. If it has a right pointer.
its right pointer's leftmost child,
1 point leftmost child.
and make that point to the left.
I,
Does that make sense?
and then make it point to the.
We want to take the.
Where would 5 go?
Where would 5 gets pointed to by the replacement node's left pointer. Or
It can't because it's the.
right pointer.
OK, and then where does the 1.5 and the 1.2 go?
It gets pointed to by the replacement node's new left pointer. And then everything
But this one had a 0 and but it had 0 and a 1.
But that's why we make the leftmost pointer of the right branch point to that.
OK. I think it's a little too advanced for me. It probably works. I bet it works, but it's too advanced for me. OK, I will take 2 more answers. Yes.
Okay, you can take, if let's say you're deleting something on the left side of 6.
Yeah.
So you take let's say you deleted 2.
Yeah.
You take 2's left child and then have 6 points to that. So 2 will not 6
Okay.
will
Okay, that's what Dylan was saying. Okay, 6 will point to 1, yeah.
And then you take one's rightmost descendant and have that point to what 2 is pointing to.
So 4 is now pointing to, huh?
No. 5 is still pointing to 3 and 3 is still pointing to 4.
Yeah.
If 1 had any right descendants,
Yeah.
one's rightmost descendant would point to 5.
Oh, okay.
But it doesn't, so 1 just points to 5.
So it does it so 1 just points to 5. Okay, in this case you do 5, 3.
No, the 4's in the same spot.
Oh, sorry. 5, 3, 4. Like that? Okay, I think that, does that work? Okay, that actually seems like it works. Okay, that was the same thing you said? Okay.
You make it the one that you
Yeah,
choose
yeah, and
the other one.
okay, and I think that actually would work. Sure. Last one. Okay. Okay. All right. Flip a coin. That's fine. Okay, that's fair enough. Maybe, yeah. All right. I mean, we don't really want to introduce randomness into this. We can help it, but okay.
The one that gets to replace this node being deleted,
Yeah.
you insert the other node into that.
Right. You do have to do some searching down it, though, don't you?
Yeah,
I mean, that's the only. Again, that's kind of the only issue is you do have to do more searching down it.
but if you do the search, it's also foolproof.
If you do the searching, it's foolproof. I'll get that. That probably will work. Yes.
That's exactly what was just described.
Okay. All right. So except for the flipping of the coin part, this is the Las Vegas method of tree design. So okay. All right. You guys came up with some great ideas. Let me present to you one that may also work and well, it does work, and it's what I would say is probably a traditional way to do it, and see if it makes sense. I think it's a little easier to understand than some of the ones that you, particularly Dylan, came up with. Okay? All right? Let's just see. All right. Let's do this. Replace with the smallest data in the right subtree. So all you have to do in the right subtree is find the smallest. That's easy. Find min is easy. Okay? The smallest in the right subtree. And then recursively delete that node, which is now empty. Is it not true that if you go to the right subtree and you go left all the way, that this will not anymore have a left pointer to it? It will always be at the leftmost point. It will have a left pointer that's null, in other words. Okay, which means that it has how many children? At most 1. Okay, so if it's got at most 1 child, isn't it very easy to replace a 1-child node? We just do the old linked list method. So let's see if this works. All it's saying, and it's actually pretty clever, I think. Replace with the smallest data in the right subtree. Okay, go to the right subtree, go all the way left. Boom. 3. Replace 2 with 3. In fact, all we need to do is replace the data. We don't even need to replace any links. We just need to say data's changed. Boom. Okay? Then recursively delete this one. This one can't have more than 1 node or 1 child because it's all we know it's a minimum of this tree. So what we have to do is just get rid of this one because we moved it up here and have 5 point to 4. Well, actually, it would be this way. You'd say 5 goes to 4 like that, and that does it. Okay, does that make sense? That's actually, I think, a fairly easy method. Relatively clever, too. Yep.
I mean, that works, but then what if 3 had like 2 children? Would you have to recurse and do that process?
How could 3 have 2 children? It's the minimum of the right subtree. Right? So if it's the minimum, we went all the way left until there were no left subtrees. Right? So yeah. So it makes sense. Yeah. Question? Was that what you? That wasn't what you'd said at the beginning, was it?
Go all the down and you put 1 at like below the smallest. Because the right is always.
Yeah, but I don't remember you saying replace this one, but maybe you did.
Yeah, but I put the 1.
Yeah. You put the 1 under the tree. Yeah, that's fine. But did you end up with this tree in the end?
No.
Okay, then it is slightly different. Yeah, but good idea. I think yours would work. I definitely think yours would work. Last question, Tar.
So basically, you're just looking for the smallest number that's greater than 1.
No, you're looking for this. Well, yeah. Is that what you were saying too? Yeah, you're looking for the smallest one in the right subtree, and which is automatically greater than 1 because it's in the right subtree.
No, but
See you guys Monday or at office hours.